Hey everyone, welcome to another week. We're almost at the home stretch here, and I might actually see some of your lovely, lovely faces next week. If you haven't already seen, there is a spreadsheet on the classroom for you to sign in during one of the days next week if you do want to come in for some extra support. So again, it's only for if you need extra help, right? I'm not teaching anything new during those times. Online learning is going to be the same throughout the rest of the month until the end of the year here, and that is that. And I did leave you the test for the linear equations unit on Monday, so that needs to be submitted by Friday. Once Friday hits, I'm shutting off the submissions, and anything that I get after is that can be considered late and will be marked accordingly. So this is actually the only thing I'm going to give you for this week to do alongside that test. The test itself isn't very long, and if you've been keeping up with the work so far, it should be quite manageable. But today we're moving into our next unit, and it's looking like it's likely going to be the final unit. We might touch a little bit into trig, and if we do, we'll only do the bare necessities of what you need, but we are running short on time. So we'll see how this unit takes, and I'm going to just do this lecture for this week. So you'll have the rest of the week to work on this, and it won't be too long. I'm breaking this up into two parts here. So this is part one, it'll be part two next week, okay? So we're looking at solving linear systems. That's the actual name of the unit that we're talking about, and we're moving into how do we go about solving a linear system? What is a linear system? What does it look like when those two things are solved, right? So we're going to just talk about just those fundamentals today. So linear systems, what the heck is a linear system? So linear system, what we can say, we can say it's a set or a group of two or more equations of similar degree. So remember, we talked about degrees as being the highest exponential term that we can find in an equation. So a linear system, it's kind of like a way to organize those degrees. So we can have a linear system, or we can have a quadratic system, or we can have there's a bunch of different systems depending on what that degree is. So for a degree one system, so for a system with degree of 1, we define it as a linear system. Because remember, we can also call anything with a degree 1 a linear function. We define it as a linear system. And it's just a group of equations. It can be, as long as it's more than two, as long as it's two or more, it's known as a system. Having just one, it's just the equation on its own. And what we talk about, we try and figure out how these systems are related. That's the kind of goal with this, is to figure out how these systems are related. And usually this relation is figuring out where do these systems, if we plot them on a graph, where do these systems intersect one another? And this is important information, especially if we consider, I'm just going to move this down as first example, especially if we consider what's going on with the pandemic right now. It's very important that we have systems to help us solve things that might be happening in the future with this pandemic. So I'll give you an example, because that's really hard to understand without any example. What I'm going to do, I'm going to plot a function, and I'm going to plot a very simplified version of what the pandemic could have looked like. So on our x-axis here, we have days, and on our y-axis, we have number of COVID-19 cases, okay? And let's assume that we handled this pretty well in BC, and let's say that this was our curve, kind of looking like that. So this is the whole flattening the curve thing. And let's say that at the beginning of this, we wanted to figure out at what point or how much do we need to flatten the curve so that it does not overwhelm our hospital system. And let's say that our hospital system, we're going to relate this to a number of COVID-19 cases. Let's say our hospital system could handle at its most, let's pretend that this is, just for the simplicity's sake, 100 cases. Obviously it can hold more, but just for what we're doing right now, let's draw another kind of function here, linear function, or a constant function technically, but linear nonetheless. And let's see that this at this point is the maximum number of cases that BC can hold for COVID-19. Well, we can say, even though these two aren't the same degree, right? Because this is kind of a curvier function here, and this is a linear function right here. We do have in a rough sense, a system of equations here. And what we would do to figure out, essentially, at what point or how long would it take before, actually, let's draw this as something different. Let's pretend that our curve didn't flatten out. It just went just like this. And it started to do its thing up here. And when we're solving the system of equations, we have two equations here. So we have our let's say, max number of beds for patients. And then we have our total COVID cases, so total cases. What this aims to solve here is the point with which they intersect. And this is important because this tells us the tipping point for our hospital system, right? We're asking ourselves with these two equations, where do they intersect? We have two systems here, where do they intersect? Because at this point of intersection, this is going to tell us really important information as to when our hospitals are going to be overwhelmed, right? Because if we only have 100 beds and our COVID cases are going through that roof, this is the point where we need to start worrying about. And we've seen a lot of that math happening in the news, and you can do a bunch of research on this if you're so inclined to figure out why solving things like these matter. So let's look at an example, more of a simplified version of what we're going to talk about, but a good example nonetheless. And we've done these before. So let's look at example 1 here. Does the ordered pair negative 311 satisfy the linear equation? So this first example we're looking at one point which satisfies one equation. And when we solved these, we said, hey, if we plug in x and y here, if we plug in our x point and we plug in our y point, and if left-hand side equals the right-hand side, then this is satisfied, right? So let's do that. So what we're going to do, we're going to take our 2x plus y equals 5, and we're going to plug in negative 3 here because that's our x coordinate. We're going to plug in here 11. And what do we get? We get 2 times negative 3 plus 11. I'll put everything in brackets and I'm subbing in. This is good practice to do all the time. It keeps things organized. 2 times negative 3, what do we get? We get negative 6. Negative 6 plus 11 equals 5. Negative 6 plus 11, well, what does that equal? That equals 5, right? So 5 equals 5. So therefore, negative 311 satisfies the equation. And that's all we have to write for this question. So this is something I would give you on a homework thing. Okay. Therefore, negative 311 satisfies the equation. And this is the essence of what we're going to eventually be doing when we throw another equation in here, except we're going to be doing things a little bit differently. And I'll show you how we're going to do that as we get into part 2. So let's look at this one here. Which of the following ordered pairs satisfies the linear equation 3x plus 7y equals negative 13? So you have 3 cases here. What I'm going to do, I'm going to separate them. And we just have to plug and play here. This is plug and play. You're just going to plug in each point, x, into the equation, and then see if it satisfies, if the left-hand side satisfies the right-hand side. Let's do a here. We got 3 times negative 3 plus 7 times negative 3 equals negative 13. What is 3 times negative 3? Well, that's negative 9. What's 7 times negative 3? That's negative 21. So we can actually you can do this just to keep this similar, because we do have a plus sign here. We'll do plus, and then I'll keep this in brackets. Negative 21 equals negative 13. Negative 9 plus negative 21. Well, positive and a negative multiplied against each other is just going to give us a negative. So we're negative 9 minus 21. So what's that going to get us? Well, that's just going to get us negative. That's going to get us negative 30. And we know that that does not equal negative 13. So therefore, not satisfied. Okay. So that one's out, right? What about B here? Let's try B. So same thing. We got 3 times 12 plus 7 times negative 7 equals negative 13. 3 times 12, that is 36. 7 plus 7 times negative 7 is negative 49 equals negative 13. 36 plus negative 49, well, that's negative 13. Good. Therefore, satisfied. Satisfied, right? I'm going to put a big nice check mark next to him. And we got one more that we can check here, right? Come on. Let's get back to my original color. And same thing. So 3 times negative 9 plus 7 times 2 equals negative 13. Let's check. 3 times negative 9 is negative 27. 7 times 2 is 14 equals negative 13. Well, hey, Yes, negative 13 equals negative 13 if you end up plugging this in. Therefore, satisfied, right? And we're all happy. We'll give that one a check mark. Okay. So XX, let's make it a red. Cool. So that's looking at the point satisfaction for just one linear equation. So point satisfaction for a system looks a little bit differently. It looks a little bit differently. And we're going to look at this in two parts. Again, this is just part one. So it's very conditional. Conditional. And what I mean when conditional means it has, when we're checking a point with two systems, the point has to match both the first system and it also has to match the second system in order for it to be satisfied. So conditional, with conditional, we'll call it conditional by the fact that a point must satisfy both equations to be considered a solution of the system. So again, think about up here. There's a point at which these two equations here, this red one here and this blue one, that they're exactly equal. And we're looking for that point. So again, this is why it's important that if we choose a point here, let's say this is 0.50 and 100, 0.50, 100 for 50 days in 100 cases. The point on this red line equals 50, 100 at this point, and the point on the blue line equals 50, 100 at that point as well. So there's where it has to be. It has to be for both cases. There has to be a point on that line that equals 50, 100, and it's going to only be 1 point for most of these cases. So let's look at an example of this. Is the point 2, negative 3 a solution of 4x minus 5y equals 23? So we'll call this equation 1, and negative 2x minus 3y equals 5. We'll call this equation 2. So the only way for this to be a solution is if number 1 is happy and if number 2 is happy. If number 1 left-hand side equals right-hand side, and if number 2 left-hand side equals right-hand side. So let's check this, right? Let's check this. And we only have one more question after this, and then the note's done. So it's kind of nice. It's a shorter one. So check equation 1. Here we go. So we have, again, our x, we have our y. Let's plug those in. So we have 4 times positive 2 minus 5 times, negative 3 equals 23, okay? 4 times 2, well, that's just 8, minus 5 times negative, well, actually, we can treat this as you have negative 5 times a negative 3. That's going to give you a positive, right? Positive 15 equals 23, okay? 8 plus 15 is 23, right? Good. So we're happy here, right? So equation 1 satisfied. But that's not good enough for if we're checking another equation here. We need to check our other equation to make sure that one's also satisfied. So let's do check equation 2. Okay. And what do? We'll do the same process. So negative 2, we'll plug in 2, minus 3, plug in negative 3, equals 5. Equals 5. We're checking our other equation here. And same thing. So negative 2 times 2, that's just negative 4. Negative 3 times negative 3, well, that's just positive 9, right? Negative 4 plus 9, or 9 minus 4, whichever way you want to look at it. Well, hey, yeah, that's 5. 5 equals 5. And we're happy. We're happy. Equation 2 satisfied. So therefore, what we can say, and I want you to put a statement like this at the end of every question just to communicate. Therefore, the point 2, negative 3 is a valid solution. Great. And that's all you have to put for something like this. The point negative 2, negative 3 is a valid solution. Let's do one more just for the sake of checking this and to give you another example of what this looks like. Split this down the middle. So again, we have equation 1. We have equation 2. Okay. And we're checking the point negative 3, negative 1. So this is our x, this is our y. Let's plug them in. So we have equation 1, right? Let's do it. So negative 2 times negative 3 plus 3 times negative 1 equals 3. Okay. And here we go. So -2 times -3, that is -6. That is positive 6. Positive 3 times -1, that's -3. 6 minus 3 is 3. Hey, satisfied, right? What do we say? So we could say equation 1 is satisfied. But we're not done yet. We're not done. We need to check equation 2. So what is equation 2 going to look like? Well, we've got 5 times -3 plus 2 times -1 equals 18. Okay. So remember, I'm using equation 2 over here. If you're confused why it's not the same thing, well, we have to check the other one, right? This is our second equation up here. 5 times -3, what's that? Well, that's -15. Positive 2 times -1, that's just -2. Well, hey, what do we get here? What do we get? We get -17. And that does not equal 18, right? So equation 2 is not satisfied, right? So this is the clincher, right? In order for this to be a solution, both of these have to be true because we're considering both of them. And is our kind of crux here. And means that both of them have to be included. Okay, and it's clearly not true here. We can't say that they're both solutions because equation 2 isn't satisfied by the point -3, -1. So what do we say? Well, we say therefore, let's follow the same thing up here. The point -3, -1 is not a valid solution. And that's it, folks. So keep your eyes peeled on that homework that's going to accompany this. This is the only thing I'm submitting. I'm going to have you do this week to move on to the next unit here. That is it. So please complete that test. That needs to be handed in by Friday. I'm not going to be taking any submissions after that. So I hope you all are having a wild week. Staying healthy, staying safe, getting outside, getting some vitamin D, biking around. I know I will be. And please, let me know if you have any questions. Let me know if you're having any troubles. And we'll get through this together. I hope to see some of your faces next week. Yeah, that's it. Okay. Bye, everyone. I hope you have a wonderful, wonderful weekend. And we will reconnect next week, either out through here or face-to-face. Okay. Bye.